Hi, how's it going? My name is Carl Diaz with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to look at a problem looking at blood flowing through a clogged artery and exactly what's going on there. This is actually what causes your blood vessels to burst and things like this. So let's get going. So we were given a question where we told that we had this unclogged area of the blood vessel that's equal to this. And then when we hit the clogged part, right, there's some plaque here in the blood, the area reduces by a fourth is what they told us. That looks like probably a half. Maybe I should make that more appropriate, maybe something like that. But either way, the area is reduced by fourth where there's a clog. And they want to know what the net force on the blood vessel is going to be. And we know that there's going to be a net force on that blood vessel because we know that net force comes from changes in pressure. Anywhere there's a change in pressure, there's a net force. That's what we know. And so we know that idea that this change in, wherever we see a change in pressure, and we know, how do we know there's going to be a change in pressure? Well, we know the blood's flowing at a certain velocity over here, and then when it gets into the clogged region, it flows at a certain velocity. Over here, it's flowing much slower than it is in the clogged vessel, right? Once it hits the clogged vessel, the area goes smaller, the blood speeds up. But what do we know about that concept? We know that the slower blood in the unclogged part actually has more pressure applying to itself in its environment, where when the blood starts to speed up, or any fluid or gas starts to speed up, there's less pressure that it applies to itself in the environment. So when the blood starts to speed up right there, there's a change in pressure, and that change in pressure is going to lead to some net force on the artery, and the change in pressure is coming from the speed difference. We know that. Again, from the concepts, go watch the fluid flow concept if you don't remember that one. So we know that the equation that we need to start this, if we're asked what is the net force, I should have put that on here, but the question is, what is net force on the artery? That's the question we're being asked. What is the net force on the artery? Well, we know net force in terms of fluids is written in terms of change in pressure on that particular area that it's going to be applied. So we know that the change in pressure doesn't happen in the area of the blood vessel. The change in pressure happens when the area gets reduced. So it's the change in pressure actually happens at the area of the clot, not in the area of the unobstructed part. So we know that when we're looking at net force, the area is going to be in terms of where the area of the clog, and it's that change in pressure. And since we were given that, it's that change in pressure that we need in order to solve this question, in order to figure out the net force on the blood vessel. Well, how do we get change in force? Well, we know, or change in pressure. We know that change in pressure can be described using Bernoulli's equation, or we know that, I said that really weird, we know that fluid flow, the change in pressure in fluid flow can be described in terms of Bernoulli's equation, so that's where we kind of want to start. Now, if you watch the concept video, you'll see that this equation right here is the one we get, and we actually use this equation to derive Bernoulli's equation, which is one up here, but now here I'm going backwards, because this is what you'll be given on your equation sheet or in the book. You'll know Bernoulli's equation. And then what you'll have to say is, hey, P1 and P2, if I can get them on the same side and subtracted from each other, I know that'll be the change, right? And then I can go ahead, and when these go on one side, everything else is going to go on the other side, and I end up with the equation here. So you use Bernoulli's equation to get P2 and P1 on one side and everything else on the other. Now we know that this blood, right, if the blood was here and decided to go like that, something like that, this is some height change that it would make. So it would be gaining some, but remember we know this is potential energy for fluid, this is kinetic energy for fluid. It would be gaining some potential energy, but that's not what's happening. Yes, you could say the blood's kind of moving a little up here, right here, but for the most part, most of it isn't, and it's not a significant, it's not moving up in height, it's just kind of flowing around that. So there's no gravitational potential energy change, so we can just omit that out of the equation. There's no change in height, so both of these would be 0. So we're left with just this equation here, where we know that the change in pressure is equal to the difference in the kinetic energy of the fluid over here versus the kinetic energy in the fluid in the obstructed part. Well, we were given the velocity of the blood in the unobstructed part. We know the density of blood, but what we don't know is the velocity in the clogged region of the artery. But we can figure it out. We know from this equation, right? This is volume flow rate. Let's just look at this, or the continuity equation. We can look at this and we can just create a relationship between the area and velocity over here and the area and velocity over here. And when we do that, we want to write this equation as the area of the unclogged velocity of unclogged is equal to the area in the clogged, the velocity in the clogged. Now remember, even though the areas are changing, so are the velocities. So these numbers still end up being the same. Again, from the concept video, go watch it. So we know we need the velocity of the clogged region of we want the velocity of the blood in the clogged region of this artery. So what we do is we just solve this equation for VCL, which is the clogged part, which is this, the area of the unclogged times the velocity of the unclogged over the area of the clogged. We know all those numbers. We know the area of the clogged part, we know the area of the unclogged part, we know the velocity of the unclogged, and now we're getting the clogged velocity. And again, we just needed that to plug into here. So now that we have that, we can plug that into there. Once we plug that into there, we can plug this change in pressure back into this equation, and that's where we get this. So we see the net force is equal to 1/2 density of blood times the velocity of the unclogged minus 1/2 times the density of the blood times this area of the unclogged, velocity of the unclogged over area of the clogged. Now, yeah, this will be one number, but we like to write in physics these in terms of just one equation. And so that's what I'm doing right here, right? And so it'll be all of this multiplied, right? Because this is the change in pressure right here. You know, the change in pressure is just equal to these. So the change in pressure, right? Times the area of the clogged part, which will be this divided by this. So it's really just, what, 10 to the negative 5 meters squared or something like that. These will end up canceling. So the area of the clogged is just that, right? And so you'll put that number in there, and you'll have the net force on the artery. All right, well, I hope this was helpful. Again, this is just showing you how to solve through this. I think the important thing to pay attention here is that this is fluid flow. We use Bernoulli's equation, continuity equation, and also the net force equation for a fluid to solve this, where the net force for any fluid system or gas system will be due to the change in pressure on that particular area. Wherever that change in pressure occurs is the area you want to use in this equation. So wherever that change in pressure occurs in that particular area, that's how this equation will set up. Bernoulli's equation let us look at the change in pressure. Continuity equation let us find the velocity in one part of that blood region, and then we were able to put it all together to get the net force on the artery. Hope this was helpful. I'm super proud of you, and I'll see you on the next video.